Oh, yes, so nice. This wedding. Yes. Oh, they are such a nice couple. Yeah, I like it. Yeah. What a beautiful couple. Yes. Oh, so nice. Okay. Yeah. So we start. Okay. So yeah, yes, starting. Yeah. Okay. Hey, ROS developers, and welcome again to a new ROS Developers Live class today. I am Ricardo, I am your host, and today we are going to continue doing some OpenAI training for that. So I apologize for the delay on starting. We are 2 minutes late. I was doing some research on AI algorithms, important stuff, that maybe will apply in some other cases in the future. But now let's start it and let's go to the starting of the thing. So for everyone that is there, I see that the people is starting to get into the class, and for the new ones, how does it works? Well, it works. We are going to use the ROS Development Studio. If you don't know what is that, then you should have read the notes on the live class. There it says. So we are going, every one of you have to connect to the ROS Development Studio, and I'm going to share with you the code, the simulation, and the notebook that we are going to use today on the class. Okay, so you're going to just to click on one link and then get access to that information. So then I will be teaching you how to do some stuff with OpenAI, and then you will be following with me and doing the same steps. So every one of you can get at the end the same results online. Okay, so let's go for that. Then let me share my screen so you can get the steps that I am doing for this. And then let me share. Okay, so what is that? So I don't know what is that. So strange thing that was there in the middle. So here we are on the ROS Development Studio. You can get at rds.theconstructscene.com. Let me go to my projects. So here we have the project for the class of today, and I'm going to share that with you. Okay, so I'm going to share a link here and copy the link and put it, Control C, put it on the chat of the live class that you are attending there on the on YouTube. Okay, so the chat does some strange things, so I'm going to shorten this link here using this tool from Google, so we can copy this link very securely here on the chat. So I'm posting now on the chat the link. Then for all of you, you need to have an account on RDS. Then if you have that and you are logged in, then click on the link that I have just shared with you. So you will receive this project on your area of the ROS Development Studio. So everyone can get in and use the same code, use the same prepared simulations, the same prepared code. That's amazing. This tool is super nice. It's good that we have invented, at the Construct. Yeah. So anyway, let me know if you have any question now. I hope that everybody is following. So I'm going to give a couple more of seconds so people follows the orders and follows the link and gets access. It's very quick. So just click on the link there, and then it will just show you on the screen on the web browser the project. Okay, so what are we going to do today? Today we are going to learn how to create an environment for OpenAI. So imagine that you have a robot that you want to train using ROS and a Gazebo simulation and OpenAI algorithms and environment. Okay, so how do you create the environment for your specific robot and task that you want the robot to solve? That is what we are going to learn today. Here on the previous class, we learned the whole training, how to perform the whole training. Now we are going to be a little more specific on the environment because it's very important. Okay, so then Yuan Zhao is asking why there are two projects. No, there should be only one, ROS Developers Live-Class. So I don't understand this question. Let me share my screen with you. So you should have received this ROS Developers Live-Class. That should be your project. And then if you are there, I don't know what you mean, Yuan Yao, sorry. So then just open the project. Let's go. open the project, and let's start. Great, you should have reached this page here. And now what we are going to do is to open the notebook. In order to open the notebook, go to Tools and then Jupyter Notebook. Then here you will have the LIVE-Class 22. Open it, also click on there. And here we have the notebook that describes all the steps that we are going to follow in this class. Okay, so I hope that everybody's following. Let me know, Yuan Zhao, you still have problems. So let's go. This is class number 22, and we have prepared this together, Epson and Miguel Angel and myself. So that's the result that you have. It could be improved a lot, but that's okay. Okay, so yeah, so I don't know what you mean, Yuan Zhao. So we'll talk later, okay? So this level is a medium level. You should be able to understand how to create services, topics, launch files, URDF, and controllers, etc., because we are going to need that for the simulation. Okay, Senthur says all set, ready to go. Very good. Let's go. Then how to use this? As always, you can watch this class by clicking on this cell and then pressing the play button. So in case that you don't have this image, because you just opened the project, you press on this cell and press the play. This YouTube video will appear that contains the lesson that I am doing. So now I'm connecting directly to my live streaming, but in the future, you can come here back and watch the recorded video of this class. Okay, so as I said, we are going to create an OpenAI gym environment for solving a robotic task. And then what is the robot that we are going to use today is this robot here. It's a hopper robot. It's a robot that has part on the top is a cube, or could be whatever, is a weight. And then it contains 3 joints there, 3 joints. Victor Romero is indicating that the project is not available. So, Victor, I don't know what is your problem there. How you click on the link that is on top of the construct here on the chat. So you go to the chat and then you will see a link that I have posted, the construct. Okay, it is now. Yeah, please don't panic. Don't panic. This is very well tested and this works. So just you have problem, just tell me, because usually it's a misconfusion sometimes. Okay, Victor, no problem. So we are going to do this to use this robot, and what we want when we launch this, what we want is the robot to keep standing position. That's the goal that we want the robot to learn how to stand without failing, because it's a robot with a single leg. So let's do one interesting thing first. Let's start. Let's launch the simulation that we are going to use. Then for that, instructions here. Let's go to simulations, then select launch file here, launch file. And then here on the launch file, let's go and open here the menu, the top-down menu. And let's find Let's Robots Gazebo. Select then the main launch file inside this package. Those are the different packages that I have provided to you. The one that we are interested in is in the Legend Robots Gazebo main launch. This is the one that contains the simulation. So press launch, and then a new window here should appear for you. And I'm going to put it here beneath here, for example. So in a few seconds, it will appear. In the meantime, let me tell you about the packages that I have included here for you on the material of this class today. Go to Tools and then open the IDE. Yeah, this message means because I was working with other projects, so no problem. It's not an error at all. So, and here I have this file that I don't need it because it's a copy that I did. So let me delete it. I don't know if you have that. If I have passed also this file, I'm not sure. Well, anyway, so as you can see, there are different workspaces. On this notebook workspace, you can see the LIVE-Class notebook. So, and the images associated to it. So that's the notebook workspace. Then we have a simulation workspace that here in the source, you have the Hopper simulation that we have created for today's class, the description and the Gazebo. So that's what we have launched, actually, this package here, and the launch file here, main. This is the one that we have launched. Okay, today we are not going to work with the simulation. I just provided because we need it for the case of today. So, but in any case, you know that you have there, you can use it for your own project, you can modify whatever. Okay, so what we are going to work today is on the Kaken workspace, because it's the one that contains ROS code. It's where you have to put your ROS code that you would use in your robot. Then you have to go here in the source and create the code here inside. In this case, it's the Hopper training. So I have put most of the code that we are going to use today is already done. We are going to do just a little part. Okay. So we are going to work here. Then let's go back to the simulation, and we have here the simulation open. And yeah, I'm going to dismiss the logs. And here you have the robot. Okay, so that's the simulation that you have obtained, should have obtained if you launch it. And if you press, as you see, the simulation is paused, because if you press play, then the robot is going to fall down like this. Yeah, well, no problem. We are going to put it back up in a few minutes. So let's go. Let's continue. So far, so good. We have the simulation running. Now, what is the task that we wanted to learn? To keep balance by doing jumps in the proper direction. So the robot has to learn how to do jumps, small jumps here, pump, 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 in different directions, so it doesn't fall down. Okay, and for that, we need to create an environment for that training work. It's an OpenAI environment. So it's an environment that uses OpenAI. And then, so that's what we are going to learn how to create. Okay, real JSK is saying this simulation is still loading here. Maybe it needs a few more minutes to kick in. No, it shouldn't be a minute. It's just some seconds to this. So in case that's happening, maybe you didn't select the proper launch file. Come back here, simulation, select launch file. Then here, come to Ledge Robots, Gazebo, and select the main launch. And then press launch again. Okay, let's continue. The environment file. So what is important about the environment is what is in charge of. What is this environment file in charge of in the whole training process? Well, it is in charge of setting the simulation ready to start. So now you see that the simulation, the robot fell down there. So when we start the training, the robot should have started in an upright position. So this environment file is in charge of setting that for every training episode that we are going to do. Okay, so that's the first thing that is in charge of. Then the environment is in charge of executing the actions decided by the learning algorithm. So this environment is the one that is say, okay, the learning algorithm says that in this situation, we should do a jump in this direction. So how do you apply this to the actual simulator, to the actual robot? You can apply this to the real robot. The same environment, you can do it substituting the simulation by the real robot if you had. Okay, so how to apply this action decided by the learning algorithm into the robot? That's exactly one of the parts that the environment is in charge of. Then another thing is that based on those actions that the environment has applied to the robot, then the robot will resort in a certain position, orientation, maybe it has fall down, whatever. Then the environment is in charge of getting the result. Whoops. So getting the result of that execution, it means how the robot is after the action. That's what we call an observation. And then finally, based on that observation, then it has to compute a reward based on that result. So it says, oh, so you have maintained this position another step after I applied the actions. Great, I'm going to give you a good reward. Oh, you fall down, then I'm going to put you a very bad reward. Okay, so those are the important things that the environment file has to do. We have a question here, Senthur, that says, I have been following OpenAI plus ROS classes. How important it is to have a good understanding of reinforcement learning algorithms? Okay, so far here is not important. We are treating here reinforcement learning algorithm as a box that we don't understand how it works, but that we plug into the system of OpenAI Gym. So this is a very good question, Senthur. This is a very good question. So let me just go a little bit deeper on this because it's important for you to understand for the whole people on the class. So if we go to the IDE and we go to the training, okay, so today we are not going to see these files here. That is the Start Training version 2, but you can open it, and let me put it bigger so you can watch it better. Then this is the Start Training. This is the file that is starting the whole training. Then in this case, as if you can see many things here, but they are very basic and very stupid. Please watch a previous class and you will see that they are very stupid. The important thing here is this part here. Here is where you inject the learning algorithm that you want to use to the whole process. Actually, if you have the implementation of another reinforcement learning algorithm, you can just substitute it here. Just substitute here and maintain the rest of the things. And then everything will work also. That is why we are not concentrating on the proper reinforcement learning algorithm, but on how to interface that algorithm with the ROS and Gazebo simulation. That's the concept. And in order to solve a task, okay? So hope that answers a little bit and clarifies a little bit. So we are not concentrated on the specific learning algorithm, but on the whole process, how to build the whole process. So afterwards, you can just test your own algorithms using the same environment. You only have to implement different algorithms or modify a little bit. Anyway, let's continue. Before anything else, we must have clear the following points. So we have to define when the robot, in case that we are applying this for this task, okay, of the robot standing still on top, straight up. But you can apply the same procedure to your own case, to your own robot, to your own situation. Then what you have to do is to define the success for each training step of the environment. In this case, we are indicating that the robot in a training step is successful if the age of the robot is above ½ meter. And if the age is below that number, we consider that that training episode is finished, and we move to the next one, training episodes. So you need to understand episode and then step, and that's those concepts that are basic in reinforcement learning. Okay, we talked about that in previous classes. Well, then another thing is that we have to define the actions that the robot can take. This is very important. You need to just say, okay, this robot, in order to solve this task, can do this and this and this. For example, in our case, what we have said is, okay, so you can move the two first joints, the one here on the top and the one here on the on the middle. Let me put it a little bit closer. So there is one joint here, another joint here, and another one here. But the actions that we are allowing in this case is turn this joint here, then turn a little bit this joint here, increase or decrease, I mean, these joints, those two joints, then don't do anything. That's another action that we are allowing, because if the robot is in good position, then we would like the robot to stay like that. Just don't move, please. And also make a single jump. Then we have encoded a whole action that is a single jump as an action that the robot can do. I mean, we are not applying any value of the joints for that joint specifically. So we are providing to the robot for this training a complete action that is make a single jump. Okay, so the actions that the robot can do are 6. Increment, decrement this joint here. Those are 2 different actions. Another one is increment or decrement, this joint here. Then do nothing with the joints, with whatever, and then do a jump. Okay, so those are the actions that we are allowing the robot to do, to perform here. Then once you have define the actions, then you have to define the observations that will define the state. It means when the robot applies any of those actions, then we have to feel what has happened. So what is the result of this? That's what it's defining the observations. And the observations defines the values, usually of the sensors, so that are important to determine the current situation of the robot. In our case, we are taking the distance from a desired point, the base roll. So those three, base roll, base pitch, and base yaw are, are values provided by an IMU sensor that is here on the green part of the robot. Then the contact force, that means the amount of force that this blue ball here is detecting on the ground. And then the joint states for the different joints of the robot. This one, and this one. Okay, so finally, we have to define the way we are going to calculate the reward. For example, if the robot is above minimum 8, then we provide 100 points. If not, we provide minus 1,000 for that specific step. I mean, not for the whole episode. Okay, so before anything else, you have to have very clear this in your own project. Okay, so once you have that clear, then it's time to build the environment file. Let's do it now. So let's go to the IDE. Let's open the IDE here, Tools, IDE, and then let's go to the, let me put it here. Let's go. I can close this one because we are not going to use it. And here on the Catkin workspace source Hopper training source, let's create this new file that is called monoped environment. And yep, okay, so let me put it like this. Okay. Oh, yeah. So, okay. So, so here it's a mistake due to the going fast. So we already have this monoped environment file. So let's do one thing. Okay. So let's just delete it because otherwise it's already done. So it's no fun. So I forgot to delete it in the last time. So it's my mistake. So let's delete it right now. So nothing happened. Nobody saw this file. Monoped environment. Done. Okay, please don't delete any other file because otherwise it will not work. Okay, so so we need to create a monoped environment file. Yeah, let's create it. Nice. So let's go to source and then let's open with a right click and here create a new file. And let's call it as it's set here on the notebook. Let's say monoped _ environment.py. Okay, so that is there. So I created the file. Now I have it. Yes, Yuan Yao, he is laughing at my mistakes. Yes. Very good. Yes. Okay, so open that file and it's empty. Yeah. And then let's start building that file. So and understanding. So the first thing that you have to do is to copy this. This is the beginning of the file that just says the important libraries that we have to import and who has created this, etc. Okay, so put it there, copy, paste, and then let's go and do the first step that is related to the environment itself. Is this section here that is about registering the environment into the gym. So the gym can instantiate it. So let's copy this first. Let's copy up to the end. Control copy, select, and then paste it here. And then let me explain you what it means. Okay, so here we are just registering into the gym of OpenAI, this new environment. And what we are doing here. So first we are providing an ID for that environment. And the ID could be whatever it is. You can put here whatever your name, monoped, biped, quadruped, whatever you want. But it is mandatory that you put a hyphen and then V and then the number of the version. Okay, so in this case it's V0. Then afterwards, you have to provide the entry point. The entry point means what is the name of the file that this environment is being defined, in which file. And the file, it's, as you can see, monoped environment. That's the one that we just created, the one that we are editing here. And then 2 dots and the name of the class that we are going to use, that we are going to build in order to create the environment. So that's the class that we have here. And then finally, the time step limit. So the amount of times of steps that one episode can be training for that. Okay, so here we have a question from RealJSK. The file should be under Hopper training folder as opposed to Hopper, as it's indicated in Jupyter. Okay, let me see. Maybe I did another mistake. Let me see. It's in Hopper training source. Yes, that's Hopper. Oh yeah, the Hopper is not there. So yeah, so I see, because Hopper is not here. So yes, so that's in an old version of the notebook. So what RealJSK is indicating that here it says Cat King workspace source Hopper. This Hopper doesn't exist here. Cat King workspace source Hopper is not there. You go straight to Hopper training. Okay, you can just double click here and then you can delete that information here if you want. Okay, so then by doing this, you have just updated your project. Remember to save, okay, here. Afterwards, when you finish, remember to save to keep your changes and your code that you are creating. Okay, so far so good. Let's continue. Then, so this class is the one that we have started to create here, okay? And that is the one that is going to contain everything that the gym environment requires for your task. Let's go and let's build it. So basically, the environment is inside a class. That's what you have to learn. And you have to register that class in the gym environment in order to be able to instantiate this. Where are you going to instantiate this? Well, in here, if you go to the code here, if you open the Start Training version 2, here, there is a place here, yes, here, where you are instantiating the gym environment that you want for that training. So in this case, you are indicating the monoped V0, and this name is the same that we have registered here. That is why, okay? Okay, so far so good. Then let's continue. Then in any environment, we have to implement several functions. There are many of them, well, not many, but a few of them, and not all of them are important. Okay, so for example, you have to present the reset function, the step function, or the render function. So these are some functions that you have to implement for your environment class because it inherits from that class. If you don't implement those, then the mother function, the function of the mother class, will be executed instead. Okay, so but basically the structure of the class is like this. Usually, this is very typical. You got the init that is we are going to put here in a few seconds. Then you have the step function that is the one that executes the step of update. We are going to see it now. Then we have the reset, the seed, the render, and then some other functions that are take action or get reward. But yeah, I haven't used this. So we have implemented it in another way. I don't know. So we are going to see now in a few seconds. So let's start with this, with the init function. Okay, let's implement the crucial ones here that allow us to train. So for the init, let's do it. So just to clarify, you don't have to do anything with this code here. Okay, it's just an example to show you a typical structure. It's a structure of a book, let's say, is a very academic structure. Then here we have done some less academic things, but more practical, I would say. So let's go for the init. Then let's copy this cell code into the class. So remember, when you copy, what I suggest you is that you just select the cell and the content of the cell here. You press Control A. This will select everything, including the spaces here in the definition. So you copy, Control C, and then you come here. Then let me go back here. And when you paste, you will see that the whole code is properly indented. Okay, because this is very important in Python, the indentation. So you can do it as you want, okay? But my recommendation, do click here until you see the cursor here, then press Control A, it selects the whole content, then press Control C, it copies the content, and then come here and come to that position there, to the beginning of the class. Then everything will be properly indented. Otherwise, you will have to do it manually. Okay, so we have that code here. That is the init function. And what does the init function does? Well, let's see what it does. First, it fetches some variables that we are going to use that are provided from the param server, from the ROS param server. As you know, ROS, the param server, already know. So those values, those functions, as you can see, are obtained from the param server, and we have quite a few here. So you can see that most of the code is just getting that information, And from where do we take those informations? Well, because here, on the config directory of the Hopper training, there is a qlearn params that you can open, and that contains all the parameters that we want to use in this training. So when we launch the whole training system, the whole training OpenAI, this function is being loaded. This config file is being loaded into the parameter server. So then afterwards, our environment can retrieve it from the parameter server. Okay, so that's the first thing that it does. Then the other thing that it does, the init, is to connect to the ROS topical services that we may need in the training for acting on the simulation. So here I'm not going to go into detail because it's too complex here. Maybe in a future class, we are going to dedicate only for that. But basically, you see, we have created those Gazebo connection, controllers connection classes that what they do, the code is here, okay? So you can check it afterwards. Gazebo connection pi, controllers connection pi, you can check that. But what they do is to connect to the simulation, to the topics, and to some of the Gazebo specific topics to reset and to put the robot in the proper conditions and to read the values. So we can use it for publishing on the joins and make the robot move. And we can use this later for reading the values of the IMU, of the joints, etc. Okay, so, and where do we do that? Well, here, in this code here. Okay, Gazebo connection, controllers connection, and then the monoped state also. It contains some functions in the inside. And here we continue up to here. Up to here, it's is the connection to the simulator. Then finally, what do we do? Define the actions space. That's what we are defining here. And what does it mean here? It means that for every environment, we have to define the number of actions that the learning algorithm can take. So in this case, as I explained before, we can take 6 different actions. You can increment a little bit or decrement a little bit this joint, the joint on the top here. Or the same for this. Those are 2 different actions, okay? One is to increment, the other one is to decrement. And I don't know why I cannot put it behind. Okay, So let's me. And then don't move, another one, and then perform the jump. So that means that we have 1, 2, 3, 4, 6 actions. So how do we create this? Well, we create an action space that is a spaces discrete. This means, hey, please, this create a spaces object that it's contains 6 values. Then we can provide. Then we are providing this in the start training here, and at the beginning, at some point, I don't remember where. Let me check. Action space here. Okay, so here is where we are providing to the learning algorithm this information that we have created here. Okay, so I have explained here more information about the different types of spaces, because in this case, the space is very discrete, but you can also create other more continuous observation space and more complex action spaces or observation spaces, both of them. For example, you can create a space box. And based on the time, I'm not going to go into this, but I think that's quite clear if you observe, if you read this code here. Let me go to one question that is from Victor some time ago. Victor says, this is great, Ricardo. I have a simulation related question. Is it possible to generate the robot URDF using Blender or another open software? I want to forget about SolidWorks. How do you do? Yes, it's possible. Yes, and many people does that. And so we don't have any tutorial about doing Blender, but we have a tutorial online that is a video in our channel that is about how to build it with SolidWorks. So for Blender, you will have to wait. Sorry. So let's continue with this. Okay. So yeah. So that's what we are generating here, the action space, and then well, the reward range is just between which values we can obtain the reward. Then at the end, what we are doing at the end of this is we are calling this seed function. That's another function that you can override, for example, from the model class of the environment. And it's a function that is here that is used to initialize a random generator. Many of those reinforcement learning algorithms, they use random numbers in order to decide a random action in the next step when they are exploring. So they need this. That is why it is created here. So in order to allow you to program really random numbers, well, as random as a computer can do. So let's copy this function here and put it here beneath the self, but remember the indentation, okay? So remember that you have to copy all the spaces, and then it has to keep the indentation from the previous file, from the previous definition. So far we have defined in the monoped 2 functions, the init function and the seed function for the random generator. Good, we have that. Okay, let's go to a couple more important functions to define. Then the next one is the reset function. What does the reset function? Is the one that restores the whole environment, the whole simulation, all the values to the initial state. So we can start a new step, sorry, a new, what's the name? A new, it's not a step, it's, so I forgot the word and I wrote it here here it was about episode, yeah, episode now, yeah. So I think I need my coffee from 2 classes ago. Yeah. Well, anyway, so when we want to reset, the reset means that we put the robot at the initial position again, so we can start training again from another, from zero, from scratch. And then this function also returns the observation data, because that first observation of the initial state is the one that is taken and used for the first step in the learning algorithm when we start that new episode. Okay, so let's copy the code and let's have a look at it. So as always, click on here, Control A to select everything, Control C, and then come here to the code. And remember to go to the beginning here of the of the file, of the editor, and then press Ctrl V. So we have this indentation properly set. Okay, all the definitions are on the same indentation level, because otherwise the Python will complain and it will not work. Okay, so this is very important of the indentation in Python. Okay, so pay attention because it may not work afterwards. So then what do we have here? Well, in this reset function, I'm going to put it lower, even lower. So yeah, in this reset function, basically what we are doing is to reset the Gazebo and all the controllers, all the positions, etc., etc. So far, we have found this way about pausing the simulation, then resetting the simulation, but then also we have to reset the controllers and the joints. For that, we were investigating about ways of doing this that didn't crash the controllers, and then we found that one that is about changing the gravity to 0, then resetting the controllers, and doing several steps here that you can follow afterwards. And after those steps, the robot will be again standing still, and the simulation is going to be paused like this here. So at the end of this reset, basically in this reset, what we are doing is just reset everything in the robot, everything in the simulation to 0 again, and then pausing the simulation. All those functions, you remember that you can find the code inside here in the Gazebo connection file, okay? And then finally, we are getting the initial observations. So we get from the simulation what is the current state, and then we provide that state here. In the end, we provide that state to the training algorithm that is here. So let me show you the connection between this function reset and the training process. Okay, so it's here on the training code, in the start training code here. There is a moment before we start with a new episode, before this, that we reset the whole environment. Okay, so this is the loop for all the episodes. And then when we start a new episode, we initialize everything. And at some point in time, we call this reset function. And we receive the state. So that's exactly what it's doing. This is calling this function here, reset, putting the robot on the proper location and getting the observation state. That's it. That, as we mentioned, the observation state is the values of the sensors that we have decided here that are the ones that we are interested in. So where was it? Here. Yeah, for example, these ones in our case. Okay, so what else? Yeah, so we have the step function and we have added that here. Then this is the step. No, sorry, that was the reset. Now is the step function, exactly. So now we have to add the step function. That's the final one, is the last one. And the step function is super important also. This is the function that is called at every training step. So the reinforcement learning loop, as you remember from the previous class, consists of a series of selecting an action, applying this action into the robot, observing the results, and calculating a reward based on that result. Then we provide this to the learning algorithm that will again select an action and apply this to the robot, etc., etc. So that function, the step function, is the one that takes the action selected by the algorithm and then applies that to the robot, allows the robot to execute this for the amount of time required, and then it gets the observation of the result of that action applied to the robot. And then based on that result, it computes a reward based on that result. And then it provides this reward to the learning algorithm, because it's the learning algorithm who is calling this step function. Okay, so let's go how it works here. So let's copy again, select here, Control A, Control C, and then come here and Control V to copy the whole step function. As you can see, it's a simple one in this case. Well, it's simple because we have simplified and we have encapsulated into some classes there that you can access later. But basically, let me show you the steps. Very simple. First, we receive a number of the action. Okay, this is the number of the action selected by the learning algorithm. It says, oh, let's try that action, number 6. Okay, and then what it does, the algorithm, is first, this is deciding to which one, this action, if it's affecting to a joint, or if it is affecting to a jump, to doing a jump. So that's the function that we have created here to do that job, to decide this action, what it's about. It's about moving a joint or doing a jump. Then once we know this information, what we do is that we unpause the simulation, because from the beginning, the simulation is paused. Otherwise, the robot will fall down while we were discussing about everything. So first, we unpause the robot, and then we apply that action to the joints of the robot, either movement or a jump. So that's what we are applying here, passing. Then this is the class. This is the class here that is actually moving the joints inside ROS. So if you want to learn how to do that, you have to go to this class here. And then once this has been applied, we wait for a certain amount of time where this action is being applied into the robot. Then after that amount of time, we pause the simulation again. Okay, because that's the amount of time that this action is allowed to be executed on the robot, no more. As you know, as you probably suspect, this running step is a parameter that you can have. And especially in robot control, that has a huge influence in the results. So that depends a lot on how the task that you want to solve and the speed of the robot that can move, or the speed that you need the robot to move. So the controllers, how well they are created. So that's quite complicated. So on the last class of this live class of this month, the last one, we are going to work a little bit on how to tune those parameters. Okay, it's not going to be next class, but after that one. So in 2 live classes. Okay, so once we have this sleep, then we pause the simulation, and what we do is that we observe. Okay, so we call this function that provides, this function here is the one that provides us in this observation, is a vector with all the information that we want to use as observation. That was, if you remember here, there were, let me see here, it's a little bit up, yes, those informations here. For your case, you have to populate that vector with the information that you would like to have. Okay, so then we get this information, and then we just process the data. It means the status of the robot, and based on that, we decide a reward. And also we decide if it is done, if it is finished, this episode or not. Because there are some criteria for calculating the reward, but there are also for indicating that this episode is going nowhere. So we better stop here, and then we start again trying. So when, for example, the robot falls down and it is on the ground, then it doesn't matter how much it tries, that is never going to get up again by itself. So we have to start from the beginning. So that was very bad. That means that we have to signal as done in this function, process data. And then we calculate the reward for that step, for that specific step. So if the robot was still standing on tip, then the reward for that step is 100. Hey, very good. You did very good this step. Please keep going. Instead, if we have a done because it has fall down, then the reward is minus 1,000 for that specific step. Okay, remember that the reward afterwards is used for computational in the algorithm of the Q-learning in this case or another. So it's used in different ways. So what else then? Yeah, so we have the observation, and then well, this we create a discrete version of the observation in order to provide this to the learning algorithm, because the observation means that all the sensors, they are very they are linear, so they deliver a float number, so they can have infinite values. But Q-learning specifically is very bad at continuous numbers, so it wants to have very discretized values for the observations and for the actions. So in this case, in order to simplify, this function is discretizing all the observations, all the values of the sensors into similar values. So we can create a state vector that is it contains all the observation values that we have, but grouped by similarities. So we don't have an explosion of different values of the sensors. And once we have all that, the state, the current state, the reward, and the done, and then here maybe some extra information that we can add, then we just return. We just return. This return is the return that we are providing to the training algorithm. So if I go here to the training algorithm, that step is the one that is executed. Let me see, where is it? Where is it? Here. It is here. Okay, so this is calling the step with the action, and then it's getting the next states, the reward, the done, and some info, exactly what we have put it here. The state, the reward, the done, and some info. Okay, and then it's receiving the number of the action. So basically, that's it. This is a support function for the get state. So it's calling the function, so you can check how it is working in the inside. But basically, that's it. So there is nothing more. So let me go down. Let me see if I'm missing something. Yeah, well, I already explained to you all that, and you have here more information if you want to check. And also explain to you all this that is about the simulation step, pausing and pausing, etc. And here, yeah, here is a little bit of code that is indicating how the get action to position is working. That you remember is here, this function here. So basically how it works, it's, let me show you a little bit. If the action selected by the algorithm is 0, then let's modify the joint number 0 with a plus a little bit more of joint increment. So let's increment that joint a little bit. Instead, if the action selected by the algorithm was 1, let's decrease that 1 a little bit. If it was 2, then increase, but joint number 1. And then if it was 3, then decrease joint number 1. If it was 4, do nothing. And if it was 5, execute the jump. So then afterwards, with this, you will get the answer here, and then you will apply to that function here, that is the one that actually performs the actions in the robot. Okay, so I put it here just to clarify, but you can check all the code is there on the classes. Okay, so I think that we have everything. So click here and press save to save this. So you can go here to File and press Save. Then be sure that there is no dot here indicating that you have changes. Okay, so if you have this saved, then let's have a look at this. So in order to do that, let's launch the training launch. So for that, let's go to Tools and open a shell. And I'm going to put here. And let's launch this command. Let me open here. Was the Gazebo. Remember to have the Gazebo screen here so we can see how it starts training. Okay, so let's put it like that. And then let's launch it. ROS launch, Hopper training, main launch. And if we launch it, then if everything is correct, we haven't done any errors. There it goes. Yes. Okay, very good. So there it goes. The robot is trying to learn by applying some jumps, some turnings into the joints also. And he is trying. And here you can see the different rewards that the robot is obtaining at every episode. Of course, as you know, from what I have explained to you, every time that the robot falls down, then it stops the episode. So you can see here that it is increasing, and that a new value of reward is generated. You can see here the values of the different trials. Okay, so if everything is correct, then the robot will eventually learn to keep the balance. Okay, so I can tell you that we did this very, very quickly, so it's not going, I don't think it's going to learn this. So probably there are so many things that we can trick there in order to make it balanced. So I challenge all of you for achieving that, for making the robot learn how to stay there and modify. I have to say that Yuan Zhao, he actually found the error of the previous class, and he has posted in the previous live class comments, he has posted the solution for the previous case of the carpool. You can have a look. There is even a video that shows how it maintains and the reward, how it evolves on the time. So I challenge you also to do the same thing. So if you achieve to make this robot train and stay on there balancing by itself while jumping, then you will receive a prize that is 1 month for free at the Robot Ignite Academy. And basically, that's what I wanted to tell you now, that if you want to learn more, we have some other courses about ROS with deep learning and OpenAI Gym for robotics 101. That's a very good introduction. And where is that? At our Robot Ignite Academy. That is an academy that we have online that we use the same procedures here. It's simulations with notebooks and step-by-step guided. Very, very nice. Here you have a discount coupon that is valid until next week. And just let me remind you that we are about to, in just a few weeks, we are going to do the ROS Developers Conference. That is a conference that follows the same procedure as this class. So we have invited several experts in ROS, and they are going to teach you different subjects of ROS using this same system. So they are going to provide you with a notebook, with a simulation, with a code, and you're going to practice with them. It's going to be on 7th and 8th of July. Please check it out because the tickets are about to expire. So to be finished. And then before we go to the questions, let me remind you that the next live class that we are going to have is about the TensorFlow with ROS. So we are going to see a very interesting example that is using TensorFlow to recognize objects in real time, obtaining the images from the camera of the robot using ROS. So we are going to use a drone that is flying, and then with the camera that is pointing to the ground, is going to perform object recognition, and then indicate at any point in time what is recognizing that in real time, connecting to TensorFlow. So it's going to be amazing and super interesting. And now that's all that I have to do. And so I have some minutes for you for answering some questions. So in case that you have ones, just let me know. I am here. Please post your questions there on the chat. I am here. And in the meantime, so yeah, that's it. So this month, we are dedicating the whole month to do ROS plus machine learning, how to apply this, but in practical things. So it's not about the theory, but about how to practically do with a robot something, do something, and how you can set your simulation, your code, so that it works together. So that's our aim for this month. And I think that we are achieving, because every week we are having more and more students coming to the live class. And then here there is one request from RealJSK that says, just a request outside of this particular class. Okay, so what is the request? Juan Yao is saying, I will add a short video this week to walk through what I have done to achieve the training in the comment section of Live Class 21. Remember to check it later. Yeah, okay, Juan Yao, he is the one who has solved the problem that we indicated last week, and then he's going to create a video and he's going to post it on the comments of the Live Class 21. Just to let you know that Juan Yao is now one of the interns of the Construct, our company, and he's working on doing many other things. So writing super nice posts about how to do things with ROS and etc. So super nice. Then come back to RealJSK. Do you think you can have a class on modeling and controlling an airship blimp? Wow, that's yeah. So yeah, we can do classes for everything, but that could be, I mean, it's out of the scope, because in these classes we are concentrated on teaching you about ROS. It means it's about teaching you how to do things with robots using ROS, because we really believe that ROS is the future for robotics. Definitely, it's going to be. So you have to learn about it, and you have to learn how to do practical things. That is our aim. Then in that case, I think that modeling and controlling an airship, I don't know, it's a little bit out of scope of ROS, unless you mention that it's controlling with ROS, but I don't know. Please send me an email with more details about that. What would be your proposal? Then we may think about it. Then Guillermo says, thank you. It was a really nice tutorial. Could you suggest some good sources for learning Python? I have problems with following all these classes and stuff. Sometimes it gets very messy and confusing. Yes. Okay. Yeah. So for that, let me just share with you my screen, because I wrote an article a few weeks ago where I was doing this. So it's about how to become a robotics developer. And in this article, really recommend you to read, because it contains a lot of interesting information about our sector. And then, well, apart from exploring why there are what is the pros and cons, so I provide a complete path about how to be developing for robots with ROS. And then the first thing that you have to do, apart from setting up, is learning. And here I propose two things that you need to master. One is learning the shell online, and the second one is to learn Python. So the shell, I mean the Linux shell, and then the Python is the Python. I really recommend you this course, that if you click here, you will see. So it's learnpython.org, and it's very good online course for free that you can do it for learning Python. Okay, so that's it. So one final thing, it says, Juan Yao says, I'm interested in live classes about self-driving cars. Okay, yes, that's a very good subject. And maybe in July, maybe we can do some of them. Any of them. In July, we are also going to do some classes on FlexB, how to build behaviors for different behaviors for robots using a behavior machine, a state machine, but very complex and super powerful. But maybe we'll have some time for self-driving cars. So thank you for the suggestion, Joao Yao. And now, guys, I have to leave. I have some other commitments. And it's been a pleasure to be here again. Remember, next live class, TensorFlow plus ROS plus Gazebo. So I wait for you there. Thank you, guys.